We're further solving problems today involving 3 dimensions. So our goal is to be able to solve problems involving oblique triangles in 3 dimensions using SOHCAHTOA. So if it's not oblique, then we use our SOHCAHTOA, the sine law and or the cosine law. And we have multiple steps again. So our first example here is determining the height of the cliff. So the brown area with the vertical lines in it, that's to represent the cliff, using the information given by the surveyor. So the blue lines at the bottom could be like a river at the base of the cliff. So he's on the other side of the river across from the cliff. The surveyor has mapped out some measurements here that we need to work with. So first of all, again, I'm going to label my vertices of my triangles just so that I have some letters to label or work with. I'm going to call this A, this B. Let's make the bottom here be C. We'll make this D up here at the top. Okay, so A, B, C, and D. Now the other thing to note, because this is 3-dimensional, but it's on a 2D page, it doesn't quite look 3 dimensions. I'm going to get you to add in the fact that the base of the cliff is meeting the water at a 90-degree angle. So think the cliff is vertical, the water itself is horizontal. So we're going to indicate that here with something that looks like a right angle symbol. So that makes triangle DAC a right angle triangle. The triangle that's laying on the water, triangle CAB, that one is not right angled. In fact, we can get that angle up here, angle C in that flat triangle. We could get that by taking 180 degrees and subtracting these two interior angles of 30 degrees and 25 degrees. And when we do that, it actually ends up being that the angle at C is an obtuse angle, which by the diagram it doesn't look obtuse, but in 3D, things in 3D, when we put them into 2D perspective, they're distorted. Like I couldn't put a compass or a protractor on there and get a measurement of 125 degrees. So the artiste people that we have in our class will understand that or can relate to that. For us concrete people, it's a little harder for us to figure that out. All right, so eventually we want to get the height of the cliff, which is DC here. Now in that triangle that has D side DC, so triangle ADC, the only thing we have are the 2 angles, which means we could get the third, but we don't have any side lengths yet. So we can use that triangle ABC at the bottom because we have a side length on that and we have multiple angles. So we can always solve for another side length, like CA, for example, because CA is common to both triangles. So let's start with the fact that we're going to use triangle ABC. So I'm going to say in triangle ABC, and this will help the reader understand what our thinking process is and be able to follow our solution. I'm going to call this side X, so the side across from angle B, or I could call it CA. Actually, maybe CA is more clear. So side C to A, so side CA, is across from angle B, so sine of angle B, which would be 25 degrees. That has to equal 25, which comes from side AB here, which is across from angle C. And that will be across from 125 degrees. So if I solve that for CA then, I'm going to multiply both sides by the sine of 25 degrees. We're going to get approximately 12.898. Now I've got a lot of extra decimal places here that I don't really need, but I'm going to keep all those digits in my calculator to be able to work with them. All right, so now I've got the length of CA. I'm going to switch triangles, and I'm going to look at the one that's vertical. So in triangle, that right angle triangle, ACD, ACDC, no, just kidding, ACD, we are going to find the side length DC. Now DC is opposite the angle of 50 degrees, which lives in that triangle. And I have the adjacent side CA. So opposite and adjacent tells me I'm using the tan. So the tan of 50 degrees would equal opposite, which is the DC, the height of the cliff that I need, over adjacent, which is that 12.898, yada, 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 in my calculator. So I still have all those digits in my calculator. I'm going to undo it. It's dividing the side DC, so I'm going to multiply both sides by that value I have in my calculator. I'm going to multiply the tan of 50 degrees by that, And when I do, I get side length DC being approximately 15.4. So I'm just going to go to one decimal place with my final answer here, 15.4 meters. So the cliff is about 15.4 meters tall. And it's a word problem, so we make sure we finalize that with a therefore statement. Okay, so looking for communication, I'm looking for organization in your solutions, being able to follow your thought process. So if you've just got a bunch of calculations randomly all over the place, I'm not necessarily going to know what you did first, second, or third. So make sure you have your answer kind of flow in a pattern. If you do need to go around to different spots on your page, you could say first I did this, and then second I did this, or maybe you want to say first I did this, and then second I did this, and third I did this. And then that way it's easier for the person to read it and flow along with your thought process. All right, example number 2. Travis wants to determine the height of a flagpole in the courtyard. He measures the angle of elevation to the top of the pole to be 25 degrees from its current location. So flagpole, ground, angle of elevation is the angle looking upward from a horizontal. So that angle with the ground looking upwards to the top of the flagpole, that's 25 degrees here. And then he moves 8 meters closer. So close, this is my flagpole, which hopefully makes a 90-degree angle with the ground. We're moving 8 meters closer. So this distance from where he was to where he ends up is 8 meters. And the new angle of elevation, diagram definitely not to scale. This should be now 55 degrees. Okay, 55 degrees. Determine the height of the pole. Well, I don't have a lot of side lengths here. So not only did we have to read the question and figure out what we need, we had to actually come up with our diagram here, which can sometimes be a bit of a tricky thing. But as I read it, I kind of generated my diagram based on the descriptions there. So let's call some points here. We've got point A, we've got point B, we'll call that C, and we'll call that D. Now, 8 meters is a side of A to B, which is a side length in triangle ABD. So I think before I can get side DC, I'm going to need to work with triangle ABD and get some values there. So in triangle ADB or ABD, doesn't matter which order we write those letters in, I can get some other angles, because right now I don't have a lot in terms of angles, but we can figure some things out. For example, this angle in here is supplementary to the 55, meaning 55 and that one in there will add to 180. So this will be 180. So I'm showing my work here. Subtract 55 degrees. And 180 subtract the 55 degrees gives me 125 degrees. Okay, so a nice little obtuse angle. That's kind of an oxymoron there. Based on that, so first I did this. Second, I'm going to get this angle up here. That angle is 180. Subtract, we can do this 2 different ways. We could subtract the 125 and subtract the 25, or we could, let's just do it that way. Subtract, because I've already got the 180 there, subtract 125 and subtract the 25 for angle A. And that gives us a 30-degree angle. Now I have that angle and I know the side across from it, which is the 8 meters. And what that will allow me to do, I'm going to solve for this side DB right here. Okay. The reason I'm going to solve for that is then I can work with triangle BDC, a right angle triangle, use SOHCAHTOA with opposite and hypotenuse. So I'm kind of looking ahead as I'm working there. All right, so we're going to work with this triangle. Sine laws are going to be applicable here, not SOHCAHTOA yet, because it's not a right angle triangle. I'm going to go with, I'm going to find the side length BD. So side BD is across from angle A, which is 25 degrees. So that's going to be sine of 25 degrees. That has to equal, side I know is AB, so that side is 8, and across from AB is the 30-degree angle, so the sine of 30 degrees. All right, and then we're going to solve for that BD. And when I put that all in my calculator, I multiply both sides by the sine of 25 degrees, and I got approximately 6.76 for that one. Okay, 6.76 meters. Now I'm going to use that triangle, so that was the third step here. Fourth, I'm going to use my triangle BCD. And from there, I'm going to solve for my side DC. DC is opposite, and I'm going to use my, not tan, I was going to put tan, but I made a mistake. There we go. I'm going to use the sine of 35 degrees will equal the opposite, which is DC, over my hypotenuse, which is the 6.76, which I still have all my digits in my calculator. Multiply both sides by 6.76. We get that DC is approximately equal to 5.54. 5.54. And that will be meters. Okay, so the height of the flagpole is about 5.54 meters, or 5.5 meters. And there we have it.